Hey, welcome back everybody. So today we're going to go ahead and continue our discussion of the physics of matter. In particular, we're going to focus in on fluids. So remember, fluids are basically substances that are able to flow from one place to another. So things like liquids and gases are considered to be fluids. And they will actually have behaviors that are very different than solids. So how are they different? Well, take a look. In case of a solid material, imagine that if I have now a solid block over here. The reason why it is going to be solid is because all of the particles that are in that particular solid are strongly connected to each other. So they're kind of like a very strong bonds, like locking chains that kind of lock everybody together in place, and they will actually act as a single unit. Can you imagine a whole bunch of people all linking arms all together into a big mass? So if somebody comes from the outside kind of pushes on one individual, that individual who gets pushed then is able to exert forces on his neighbor and bring the neighbors along in response to that push. So if I were to go ahead and exert a force now, okay, as it turns out it doesn't matter where I push along this block. So if I push here, okay, then the whole block moves as a whole in unison. Or if I push down here or up here, it doesn't really matter, okay? So the location of the force being exerted doesn't matter because everything kind of moves along as a single unit. And so it is very convenient then to imagine that all this is just a single point that then moves in unison. So that's the behavior of solids, and with that we can actually apply again the equation of kinematics and dynamics to describe how do we respond to forces. However, when you look at fluids, they no longer have this particular behavior. So imagine now if I were to imagine a sample of fluids that is in this imaginary box. We're not going to worry about the container, but the fact that we have a group of material over here. So now the particles in here are now very weakly linked to each other. So there's very little connection, so to speak, between the individual pieces. So now when I apply a force to a particular part of the fluid, then only the part of the fluid that comes in contact with the force is going to feel the push, so to speak. So when this part gets pushed forward, it is not able to drag the others along with it. So although there is a little bit of dragging, it's really insufficient in terms of comparison to solids, that the whole system doesn't all move in unison. Only a small portion of it kind of moves. So you can imagine as you continue to push, what might happen is that you might actually create a little dimple in here where only the part of the fluid that you come in contact with begins to get pushed out of its way, for example. So really in this case, depending on where you push, whether you push it here or here or here, you get slightly different reaction from different parts of the system of fluids. So in this case, it is important then to look at the contact between the force of being applied and the actual fluid system itself. And so that's why the idea of area of contact becomes very important, because that's the part where the fluid actually feels the force being applied to it. And so we then define this quantity that we call pressure that will now allow us to understand the behavior of fluids as it interacts with its environment. So if you recall, pressure is defined as capital P equals to force divided by the area of contact between the environment and the interacting fluid. Of course, if I were to rearrange this, I can now also write this in terms of the force of interaction, be equal to then pressure times the area of contact. So we can now look at the relationship between pressure and force of interaction, so to speak. And the way we can see this in action is look at a specific example. Let's say I look at the pressure that is being exerted by a person on the ground, let's say for example. So if I were to look at a person, let's say that has a mass, it equals to, in this case, let's take a look at, instead of the mass, let's look at something a little bit more convenient. So since we are looking at the weight of somebody, let's take a look at the gravitational force. Let's say that somebody has a weight of 160 pounds, for example, 160 pounds. And let's say this person is basically standing on 2 feet, making contact with the ground with both feet. And let's say that the person is wearing shoes, so that the shoe will have a certain cross-sectional area of contact with the ground. So let's say that the area of the shoe, is roughly equal to, what's a good one, 20 square inches, each. That seems like a pretty reasonable number. So you can look at the dimensions of a shoe. If you multiply them out, you get about 20 square inches as a nice sized pair of shoes for somebody who's about 160 pounds. So with that in mind, you can now ask, well, what is the pressure that this person is exerting on the ground as he stands on the ground, in contact with the ground? So in this case, pressure then is going to be equal to force of gravity divided by the area of contact. Now, of course, there are 2 feet, so there's going to be 2 shoes, and so the total area of contact is going to be what? Twice this here. So the idea is that 160 pounds is now going to be spread over 2 of these shoes. Or think about this. That means that each shoes will really exert, will support about what? Half of the weight itself. So you can think of this as now 160 pounds, over 2 times the cross-sectional area of the shoe, which is now 20-inch square. So if you work all that out, you end up with about 4 pounds per square inch. We basically simplify this in saying that this is now for PSI. So PSI really are the units for the US customary system of pressure in units of pounds per square inch. That's where PSI actually comes from. So now the person is exerting about 4 PSI on the ground, standing on 2 feet. What would happen though if that person all of a sudden lifted up 1 foot and decided to stand on only 1 foot in contact? In that case, what you find is now the pressure is going to change while the weight stays exactly the same. So now the new pressure is going to be still force divided by area, except this time now you only have one area to worry about. This is now 160 pounds, divided by only one of the shoes, so only 20 square inches. This now gives you 8 PSI. So what happens is, although the weight of the person remains the same, you can now double the pressure by making the area of contact half as big as before. So by standing on 1 foot, you now increase the pressure on the ground by a factor of 2. Taking this a little bit further, what if then, instead of having nice flat shoes that make contact with a large surface, what if the person were to now put on stilettos, high heel shoes, for example? And let's assume that he's going to put on this high heel shoe and he's going to stand on 1 foot and have all his weight concentrated on the heel of that particular shoe. Let's see what happens in that situation. In this case, what you find is that the area of the heel now of that the stiletto might actually be relatively small. So that heel might actually look something like this, where the dimensions might be about 0.5 inches on both sides. Imagine if you had a square cross-sectional area for the heel, so it's about ½ an inch. And so you can also use a circular shape and use that as a diameter, that's fine too. But in this case, imagine if I have a square like this, then the area would then be 0.5 inch square, or 0.25 square inches. Now with that new area, when you look at now the pressure that is going to be exerted, pressure is now still 160 pounds divided by now 0.25 square inches. You find that if you work that up, you end up with 640 PSI. And that is why it is extremely uncomfortable if somebody were to step on your foot with the heel of their stiletto rather than the whole foot itself. You can kind of see a big difference between the pressure that's going to be exerted across the surface area of contact. And so whenever we talk about pressure, we have to worry about the area as well as the force of interaction between those two surfaces. And so that's just kind of one quick example. You can actually see this in real-life application as well. Think about the tires that you have in your car and the air pressure that is associated with those tires. So notice what happens as you pump more air into the car, then of course the pressure inside builds up, And as it builds up, what happens to the car? The tire begins to expand, and what happens is that, the tire initially might look something like this, but as you begin to feel it, as it bulges upward, it actually begins to, change its shape a little bit so that the area of contact between the tire and the ground changes as well. So if you have a certain pressure in your tire at this point, and as you pump more air into it, the pressure now increases. What happens is the tires are what is supporting the weight of your car. Imagine if you have your whole car has a certain weight. Well, you have 4 tires that are on the car. So each tire basically supports 1/4 of the weight of your car. And so that force, of course, is going to be such that it is going to be the interaction between the tire and the ground itself. So the weight of the car coming down would then have to be supported by a normal force pushing back up. And the force that the tire pushes on the ground with depends on the pressure that is inside the tire multiplied by the area that you have here. So over here, if you have a relatively large area of contact right across here, and over here now, the area of contact is now smaller, what you find is that the small pressure inside the tire multiplied by this bigger area of contact will give you the same force as a bigger pressure inside the tire across a smaller area of contact. Both of which would then equal to 1/4 of your car's weight with passenger and everything included. So that's the idea behind this particular combination here. As pressure changes and area changes, those combinations can give you the same force based on one getting bigger, the other getting smaller, and so on. And that's why, for example, in terms of wear and tear on your tire, if you have tires that are constantly flat, what will happen is that it will make a bigger contact along the ground, and what will happen is that this edge of now your tire can get worn down much quickly, and then you can now have uneven wearing. Whereas you want really the treads of your car to be making contact with the ground so that you have wear along here and not on the walls of your tire when they're kind of running flat. Okay? That's the reason for that. All right, so the idea is to make sure you understand the difference between force and pressure. They're not the same thing. They're related, but they're not the same thing. Okay? All right, once we have that, the next thing we might want to do now is kind of look at another example of how to utilize this idea of pressure calculation. In this case, instead of looking at physical objects, let's take a look at something that's a little bit more fluid. Imagine what happens if you have an aquarium, and you go ahead and fill the aquarium up with a certain amount of water. And as the water sitting in the aquarium is going to be pushing down on the bottom of the aquarium, you might be interested in finding out how much pressure is being exerted on the bottom of your aquarium. Okay, so let's see what that looks like. So imagine now, if I have an aquarium, and we have a certain physical dimension that looks like this. Imagine we go ahead and do it so that I can try to draw this three-dimensionally. So there's going to be a certain length here. So let's say the length of your aquarium is relatively big. It's a pretty big aquarium, 1 meter along here. And the width of your aquarium over here is, let's say, 0.5 meters, so half a meter here. And let's say you can go ahead and fill this up with some water. And so you fill this with water, the water will come to a certain level here, sitting here, for example. And let's say that the height of the water inside the tank is 0.5 meters as well. Okay, so you have an aquarium with this much water sitting in there, sitting in there. So the question then is, what is the pressure that the water will exert on the bottom of the aquarium? Well, it's not that bad. We have a definition for what pressure is. We know, for example, pressure has to equal to the force of contact divided by the area of contact. Okay, area of contact. Now, the force of contact is, well, what is it that's pushing on it? Well, it's really the weight of the water sitting on it. So this is really the force of gravity acting on the water, divided by the area, of course, is just the length of your aquarium times the width. So in this case, I'm just going to use these symbols. I'm not going to worry about the numbers for now. So it turns out it'll simplify a little bit later on. So now, the next thing we have to ask is, what is the weight of the water? How do we find the weight of water that's sitting in there? Well, you know what weight is, right? Because if you look at force of gravity, that's equal to just mass times gravity. So I really need to know now the mass of the water sitting in there times gravity. Because I know that this is water, I now can use the definition for density of water, because that's the number that I can actually look up to relate it to the mass. So if you recall, density of water, in this case, we're going to call this the mass density, and so I'll go ahead and abbreviate this using a little m here to remind us that we're really interested in the mass of the water. This is now going to be equal to mass divided by volume. And we know that for water, it has a very nice value of 1.00 grams per cubic centimeters. Okay, so we know that. Now, of course, those units are convenient if I have a small amount of water, but here I'm looking at something that is in units of meters in terms of dimensions. So chances are, instead of looking at centimeter unit, I am much more interested in meter unit. And if that's the case, I probably would want a bigger size value for my G as well. So I'm going to go ahead and make a conversion. So I'm going to go ahead and convert from grams to kilograms. So 1 kilogram is now 10 to the third grams. And I'm also going to convert, from cubic centimeters to cubic meters. So 1 cubic meter to cubic centimeter. Now, cubic centimeter is going to be 110 to the second power centimeters per meter. But then you have to take this and cube that. So it's multiplied by itself 3 times. So this gives you 3 times 2 gives you 10 to the 6th. This is 10 to the 3rd, so it cancels out with 3 of them. This gives you a total of, in this case, 1,000 kilograms per cubic meter. So centimeter cube cancels there. Grams cancel here. You have kilogram per cubic meter. So 1,000 kilograms per cubic meter. So interesting enough, if you have enough water, it's pretty darn heavy. In this case, the mass is 1,000 kilograms per cubic meter, or about what? 2,200 pounds per cubic meter. So quite a bit of weight or mass in this case. Once I have that, I can now calculate the mass of something. In this case, the mass is equal to what? If I rearrange this, this is really just the mass density times the volume. So somehow if I know the volume of the water that I'm looking at, knowing this mass density, I can now calculate the mass of that water. So let's go ahead and put that in here. In this case, the mass of the water then is going to be the density of the the mass density of water, times, well, volume, in this case, is a rectangular block. That's just length times width times the height. This is length times width times the height. And of course, I have to multiply by gravitational acceleration, g over here. Okay? G over here. So once I have that, I can now go ahead and place it into my formula for pressure. So now I look at pressure. Pressure is equal to force divided by area, or in this case, force of gravity is just this thing over here, density, mass density of water, times length, times width, times height, times g, divided by the area is now length times width. So notice that, okay, the length and the width actually cancel out. That's why I didn't even have to worry about putting numbers in, because they will actually cancel out in the long run. So all I have is now for the pressure of this fluid water sitting on top of the bottom of this tank here, it's going to be given by the mass density, okay, times gravitational acceleration times how deep this water is, so to speak, or how far above the surface does this particular fluid, okay, go up to. So this is now very important in figuring out what that pressure is. So for our value, in this case, I have now put the numbers in, okay, 10 to the third kilogram per cubic meter, okay, times g of 9.8 meters per second squared, okay, and then times the h, okay, in this case, it's going to be about 0.5 meter. And if you work this out, notice what happens. In this case, the kilogram meters per second squared, this combination gives you the units of newtons, okay? And then this meter would then cancel out one of the meters down here, giving you meters squared at the bottom. You now have newtons per meter squared. Oh, that's the combination of units that you want now for pressure. It's a force unit divided by, okay, divided by an area, okay, divided by the area. And if you work that out, you end up with, okay, a number like, in this case, okay, 980 newtons per meter squared as the final answer. So notice in this case, I now have pressure in units of SI system type of values, where I have Newton now and a meter squared. And this allows us now to actually define a brand new quantity. We can now define the following. In this case, if I take, okay, the unit of Newton and meter squared, if I apply 1 Newton of force per square meter of area, this is now called the Pascal, okay, 1 Pascal. So the abbreviation for that is capital P, lowercase p. So 1 Pascal is equal to 1 Newton per meter squared, okay, 1 Newton per meter squared. Oh, wait a minute, something looks kind of fishy over there. Let me check this real quick. Okay, so basically 1,000 times 9.8 times 0.5, that should be 4,900, okay? Something's wrong there. So, there you go, 4,900, okay? 4,900, okay? Newtons per meter squared. Just have to worry about punching things in the calculator, okay? All right, in this case, that means when we rewrite this, this is now going to be equal to 4,900 pascals, or if I use the metric prefix, this can be now written as 4.9 kilopascals. Okay, so those are the units for pressure in SI system. Okay? Pascal or 1,000 Pascal, kilopascal. All right. So notice in this case, I had to kind of convert the weight, okay, into mass first, and then from there calculate the force and blah, 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 and then I finally got my answer. As it turns out, if that's the case, since I am looking at really the force that the object is expressing, and this is the force of the fluid that is going to be pushing down on the area, it might be useful to define a slightly different quantity than using the quantity of mass density. In this case, something you see is that you can now use something called the weight density as well. Okay? So you can also talk about now, okay, for water, okay, the weight density. Instead of the mass density, you can now talk about weight density. Well, in this case, if you look at weight density, that's just going to be what? The mass of something times g. So this is really just mass times g. That's the weight divided by the volume, by definition. And the good thing is that if you notice, I can now combine this part right over here. The mass divided by volume is just now my what? My mass density. So this is really just the mass density times gravitational acceleration g. Okay? So if I go ahead and put that into this particular situation here, I can then have 1,000 kilograms per meter cubed times 9.8 meters, okay, per second square. But work all that out, and now we have, okay, units of, okay, roughly 9,800, okay, newtons per meter cube. So this is now, okay, in units of newtons per meter cube, of weight or force over volume. This is now kilogram per meter cube, which is mass over volume. So this is the amount for water in terms of mass. This is in terms of, okay, weight. So interesting enough, if I do that, I can now kind of see what's going on over here. I can now summarize this in a bit of a simpler form. So in general, you can now look at the pressure, okay, of a particular fluid that is sitting on top of the surface by looking at its mass density multiplied by G, multiplied by, okay, how deep it is, or how much of it is above that surface that it is pressing on. Or if I look at this, the mass times G, okay, that's just your weight density. So I can actually simplify this one step further. I can now look at weight density times the height. Either one of these can now be used to calculate the pressure of a fluid sitting on top of a surface based on how far up above the surface the fluid is going to be found. So you gotta have deeper pool versus a more shallow pool, then the pressure is going to be different. So interesting enough, the pressure depends on the amount of fluid you have above the area of contact. And that makes sense, right? The higher up this H is, that means the more stuff you have piled on top, it's going to weigh more, it's going to have a greater weight, therefore it's going to be a greater pressure for the same area that you're going to be pushing down on, okay? And as it turns out, it doesn't matter what the area is going to be. It's actually just going to matter about the height, because as it turns out, the area actually cancels out over here. It cancels out. So you can use either one of this, depending on whether you use the mass density or the weight density. Okay? Either one of this will allow you to calculate the pressure at a certain depth of a particular fluid. All right, so again, it's a matter of convenience. So with this, we're going to go ahead and summarize some of the things that we've talked about in terms of some common behavior. And fluid behavior has been studied by many, many people. One person who is really well known for studying fluids and understanding the properties of fluid was a scientist by the name of Pascal, and he came up with a very special principle that kind of helped us describe and understand what's going on with fluids. In this case, we're dealing with what we call static fluids, meaning that we're looking at a fluid that is not moving, that is enclosed by some sort of container, and it stays sitting there, it's not moving, a static situation. When it starts to flow from one place to another, then that is a slightly different situation that we're going to have to cover in a slightly different way. So we're going to worry about only static situations. So in terms of static fluids, okay, that means that you're now looking at a fluid that is enclosed in a system and it is not moving. Okay? It is not moving. And so we can now discuss its behavior using Pascal's principle. Pascal's principle. Okay. And in terms of Pascal principle, there is actually two different pieces that we are going to be interested in. We can call these Pascal's first law and Pascal's second law, for example. Kind of like Newton's three laws of motion. So let's take a look at the first one. The first one is called Pascal's first law. And in this particular law, Pascal tells us something about what happens when the pressure in a particular fluid changes. In other words, if something from the outside actually pushes on the fluid and causes a change in pressure, in other words, you increase the force of action, and so what happens to the rest of the fluid? So we can go ahead and summarize it in that way. In this case, what you're told that a change in pressure, let's go ahead and write it down, at any point, in an enclosed fluid. So enclosed means it's basically container to container and it's not moving. So it's an enclosed fluid, at rest, so it's not moving, is transmitted, unchanged. That means it doesn't go bigger or smaller than what it is. It's basically the same value to all points in the fluid. Okay? That's an interesting situation. In this case, it is almost as if you're looking at a solid material. So as it turns out, okay, we're going to assume certain things about a fluid. In this case, we're going to imagine that if you look at a liquid, for example, this seems really obvious. A liquid is what we could call an incompressible fluid. So that means that as you try to press it, you can't actually change the volume very much. So in a solid, for example, if I have a solid material, okay, if I basically were to hold my hand out so that one hand touches the shoulder of one person, the other hand touches the shoulder of the other person, and I keep my arms rigid, if somebody were to go ahead and push that person on one end, that push actually gets transmitted to me, and I feel the push almost simultaneously. And however hard that push occurs there, I will feel the same size force acting on me, pushing in that direction. In the same way, if you have a fluid, okay, if you push on one end of the fluid that is in a particular container, that force that you exert over a certain area, that pressure that you exert onto the fluid, gets transmitted all the way throughout the fluid, with the same value without changing. That's what this is talking about. And what happens is this: as that pressure difference, as that change in pressure actually occurs, it will not always exert a force on the surface of contact that is perpendicular to the surface. What do you mean by that? Well, one example you can kind of see might look something like this. Here I have, a contained fluid, in this case water, inside two syringes like this. So notice over here, the syringe has a lot more water in it, the plunger is this far up. This one has just a little bit of water, and they're connecting with this tube that has water in it as well. So this is now an enclosed fluid, and it is initially at rest, not moving. So what I can do is I can then push with a force on this side. That force that's transmitted over a certain area, that will then increase the pressure on this side. That pressure that I basically introduced would then find its way all the way throughout the liquid to the other side, so that right over here, all of a sudden, that change in pressure also exists and occurs right here simultaneously. When that happens, it would then exert a force, across that particular area in that direction. So you can actually see this happening. Now, what I'm going to do is actually use my chest to push the plunger, because I want to make sure that the rubber hose doesn't get disconnected and squirt water all over the place. So notice what happens to the other plunger as I exert a force on this side. As I push on this side of the plunger, notice that that plunger begins to move forward. So that means that I'm actually transmitting my force through the liquid by this change in pressure that I exert on one side. And that pressure gets transmitted all the way through to the other side. You got to see that. So it's acting almost as if it is a solid that can shift all at once from one side to the other. And in this case, what you find is that when the pressure exists over here, the pressure is now across every part of the container wall, so to speak. And the force is going to be always acting perpendicular to those walls all around here. And then as it works along here, that's the one that pushes the plunger out in this direction. Sometimes you actually see this not only in liquid, but you can also see it in gases as well. Gas is a fluid after all. So some of you, if you kind of experienced this before, imagine going into a real fancy hotel that has these really nice fancy restrooms. And the restroom will have the actual toilets on the inside, and then there is an intermediate chamber. It's like a little makeup room that has a little mirror, and then you have to make it stuff. And so there's a room that basically is in front before you get to the actual bathroom itself. And there's two doors that connect to them, and they're usually swinging doors. So imagine now if you push on one of the opening door on the outside, as you push that swinging door out, what you notice is that the other door on the other side actually moves at the same time. So as you open this door, you can see that the swings over slightly on this side. And that's because of Pascal's principle. As you exert a force on the door across a certain area of the door that changes the pressure of the air inside the room, that pressure change is transmitted all the way to the other side, and that pressure change now acts on the second door, exerting a force on it, pushing that open. So next time you're find yourself in that situation, see if you can notice that. So that's all part of Pascal's first law. Also, Pascal's first law is very useful in looking at something that we have talked about when we talk about energy and work. And that is the idea of simple machines. So we talked about mechanical simple machines, where we can actually manipulate the size and direction of forces using mechanical pieces like levers, and ramps, and so on and so forth. In this case, I can actually use fluids to basically manipulate forces and a motion in terms of work that is done. And so we can actually have a particular type of simple machine called basically hydraulic presses. So hydraulic press is a type of simple machine that utilizes Pascal's principle, first law. So how does a hydraulic press work? It basically works something like this. Imagine if I have a tube that is in the shape of a U like this, okay? And let's say that the tube is open on the top on both sides. And let's say I'm going to go ahead and put a little cap over here. So this could be a disc that is actually now movable. So the disc is about the same size as the internal diameter of the tube. It can actually now move up and down here. And then what I'm doing is fill this part here with some sort of a liquid. So in this case, some sort of fluid. So it could be oil or water, whatever. So this is going to be some fluid in here. In this case, I'm going to look at this in terms of a liquid. Okay? So either oil or water. Both of them will work. Okay? So let's see what happens in this situation. Well, what you can find is that in this side, there's going to be some area, it's called the area 1, for the size of this cap, which could be a piston, for example. And there's going to be area 2 on this side. That will give you the cross-section area of the piston or cap on the other side. It can now move up and down. Imagine what happens now if you were to go ahead and exert the force onto these caps. In this case, as I push down over here, let's call that force 1 going downwards. Okay? So when I exert a force across a certain area, a certain pressure will build up behind the piston right here. So the pressure there is going to be pretty easy. Pressure 1 is just equal to what? Force 1 divided by area 1. Okay? So somehow there is now this pressure 1 right behind here due to the force 1 pushing down on it. Now according to Pascal's first law, this pressure, once you exert the pressure on there, that gets transmitted throughout the liquid, undiminished everywhere along the line. So everywhere along these walls, there's going to be that pressure, exerting forces on these walls outwards this way. But the key is look at what happens when it gets to this point over here. When it gets to this point over here, there's now this pressure 1 here that is the same as this pressure 1 on this side. Okay? So as this pressure 1 gets over here, it's now going to go ahead and exert a force on the area and create a force in the upward direction. So in this case, there's not going to be a force on this side. Let's call that force F2 because this is the force that is now being experienced by this particular cap here as it being pushed upward. So here, I can actually look at the pressure that will allow you to actually exert this force across this area. So you imagine now P2 over here, based on the fact that this is 2 here, that's going to be F2 over area 2. But we just saw that this pressure must be the same as the pressure that's on this side. All the pressure along here must be the same. So really this is also equal to what? Just pressure 1. That's the whole gist of Pascal's first law. The pressure inside here doesn't change as you press down here. You change the pressure here, that change gets transmitted all the way through over here. So now you kind of see what happens. If this pressure now, if this pressure is the same, that means that on this side, force 1 divided by area 1 must then equal to, on the other side, that must be equal to force 2 divided by area 2. And what I can do now is I compare the two forces, the force on one side compared to the force on the other side. Also notice something interesting. The direction of the force has changed. Here I push down on this piston here, and this piston gets lifted upward. So that's one of the classic example of a simple machine where you change the direction of the force. So let's going to rearrange this. And if we really are interested in the ratio of the output and the input. So imagine that you're coming out on this side, there's a force F2 here. You compare how big this force is to the force that you put in, there's your F1 over here. So that's going to be equal to, so in this case, if I bring F1 down here, I can bring A2 up to here. So on the other side, I now have A2 over A1. So the relative sizes of the surface areas of your movable pistons will dictate the relative size of your forces that you get on the two sides. If the areas are the same, you get the exact same force in and out. What it means is that all you're doing is changing the direction of the force. That's pretty straightforward. But if the areas are different, then you can now magnify your force. In other words, you can now have a mechanical advantage. So let's see what happens if I were to go ahead and draw a picture where you can actually have a difference in size now. So let's go ahead and bring this and kind of remind us what it looks like over here. So F2 over F1 equals to A2 over A1. Let's go ahead and redraw this a little bit. Except this time now, instead of having same size area, let's make it so that one side is bigger than the other. So imagine now I have a narrow tube over here. That looks like this. And going on to this side now, it merges into a much bigger tube. So now I have obvious difference in size. So here I have a cap right here. I have area 1. Now I have a cap here. And we now have area 2. So in this case, if I were to go ahead and push down with force 1 down in this direction, what you find is, okay, I now get a force F2 out on the other side, that is going to be much bigger, okay, much bigger, based on this ratio. So notice in this case, okay, if I have a really big area divided by a small area going in, then obviously I would have to have a big force over a small force that way. Okay? So by increasing the second area here, I now have increased, okay, my force output. This is a little bit different than the way you see simple machine like a lever, for example. Okay, so you have to be very careful. Okay, in the simple lever, the input distance bigger will give you a bigger output, okay, force. Here, the input area is actually smaller, and you get a bigger output force on the other side. So you have to be a little bit careful about what the other side. Now, what are we getting? Why is it that I am so fortunate to get this huge force coming out? Well, obviously I have to sacrifice something. So what is it that I'm sacrificing? As it turns out, I'm actually sacrificing distance over which the force acts. So let's see what that looks like. Imagine if I go ahead and extend this up a little bit. Okay, so the rest of the two. So let's see what happens. As I push this down, okay, what you find is as I push this down, maybe down to here, for example, okay, I have now acted over a certain distance. So let's call that distance 1. So here's the force, multiply this distance over here. And this distance is actually pretty big, okay, because I have to push on it. And in this case, when I do that, I have now moved all of the fluid out. So this is now the volume of fluid that I kind of push out of my way in order for me to push this plunger from here to here. Well, guess what? All the fluid, as I push it up, must now travel to the other side. And as it turns out, it must then raise this upwards. In this case, I have to displace an equal volume of fluid. And the way I do it is I actually move this up just a little bit, okay, to here, so that when you look at the distance that you move up, this is now a much smaller distance. But if you look at the amount of fluid that you displace, this is the exact same amount of fluid that you push out from the other side. So here, when you look, here is a small force times a big distance that tells you the amount of work that you did in moving that fluid out of the way. Here, I now have a big force, but working over a small distance, so the product still gives you the same amount of work. So you're not getting any extra work. You're still using the same amount, you're doing the same amount of work, but you're changing the way that you're doing the work. So instead of exerting a small force and moving something over a big distance, you're now using a big force and moving something over a small distance. Okay? And where would you see something like this? You can probably see this in, let's say, an automotive garage, for example, where they use these hydraulic lifts to lift up cars so they can work underneath the chassis of the car and so on and so forth. Okay? And the way they usually do it is, instead of physically pushing it down with a plunger or something, they actually connect this up to a compressor. So imagine now you connect this up to a compressor, okay? And the compressor would have a certain amount of fluids in there. So in this case, instead of putting a cap right over here, basically, you fill this up with something like oil, for example. Okay, so here is now that fluid in here, and basically the compressor would now allow you to pump air into this particular compartment here. So as you pump air into it, the air would then increase the pressure above this liquid, and as that pressure exerts force down on the liquid, that's now your F1. That force then gets transmitted all into here, and where the pressure that you build up, and that pressure would then allow you to get a much bigger force coming on the other side. And so when you want to lower it, all you have to do is open this up, release all that air out of there, and as you release the air, now the pressure decreases, and the weight of the car now basically pushes it back down, and then brings the level of liquid on this side back up, okay, in the reservoir. Okay, so you kind of see something like that. And you can actually see this, okay? This is an example of a hydraulic jack that you would use, okay, to, let's say, lift up your car to change a flat, for example. And basically, this is a handle you put into here, for example. And as you go ahead and push down like this, you're not exerting a force, okay, over a smaller tube right here. So this is your input tube, which has a small cross-section area. This is now a much bigger cross-section area. So now you can actually, okay, use this now to lift up on your car. So the amount of work that you do is the same, but the force that you exert is now small, but it moves over a big distance, while the force coming out is pretty big, but it's moving only a small distance, and so on and so forth. Okay? And once you have it lifted up and you want to kind of release it, then what you do is, okay, take this here, okay, and kind of just release the gas in there, and as you do so, you allow the plunger to go back down, push the gas back in. Okay? All right, so this is an example of a hydraulic jack. allows you to basically change a flat tire, for example. Okay, and there's going to be oil in there, just like in that reservoir that's shown here. Another example to show you that there is indeed a sacrifice of force is that you can actually look at something like this. So if I were to go ahead and take some water into here, okay, in this case, basically what happens is that as I push on this side, I can now exert a force on this side, but notice that I have a big area on this side. So that big area, a force that I push in has to be relatively big. And what happens, that builds up a pressure behind here, that pressure gets transmitted all the way to over here. In that case, the area over here now is kind of small. So that means the output force here is also going to be kind of small. But here's the thing, I just need a small force, but I want to move the water over a much bigger distance. So if I were to push this just a little bit in, the water shooting out of here can go a very long way, and it will basically conserve the amount of work that I do. Okay, overshot, but that's the idea. So this is now kind of working backwards, kind of like a class 3 lever, where you sacrifice force to gain distance out of something. So by pushing hard on this side, moving the water over a small distance, I can now exert a smaller force here, but move the water over a much bigger distance, going to the other side. Okay, I'll go ahead and work that a little, clean up a bit. All right, so that's the idea. Okay. All right, so that's basically Pascal's first law. So what about his second law? Let's take a look at his second law and see what he says. In the case of Pascal's second law, what he's going to tell you is that it is related to what we saw earlier. That if you were to look at a fluid, and if you were to go ahead and look at what happens with the pressure as you go deeper and deeper into the fluid, what you find is that there's going to be an increase in pressure as you go deeper and deeper into the fluid. The question is why? Why is it that if you go deeper, you have a greater pressure? Kind of like when you go swimming in a swimming pool, for example. You probably experienced this before. Right? When you dive into the swimming pool, for example, if you want to kind of retrieve a coin at the bottom, as you go deeper and deeper and deeper into the water, you feel like your head is now being compressed by the water. It doesn't feel very comfortable. And this is especially true if you go really, really deep in the water. And so what's going on in this case? Well, as you go deeper and deeper into the water, you now have more and more water above you pushing down on you with its weight. And that force, that weight adds to the pressure that is now being exerted over your surface area of your body and so on. So let's see how that works. Okay? So in this case, let's take a look at Pascal's second law. Okay? In Pascal's second law, the way we're going to go ahead and show this is to look at the following. Let's imagine that we have a liquid here. So here we have, let's say, a fluid. In this case, it's easiest to look in terms of liquid like water, for example. And I'm going to go ahead and look at this as the top of the liquid, and then, of course, it goes down deeper and deeper this way. Okay? And let's take a look at a particular chunk of this liquid. So imagine I can have, let's say, a cylindrical sample of this liquid like this. Okay? So here's a cylindrical sample. So that over here, there's going to be a certain amount of cross-sectional area. And it's the same area down here of the cylinder. And we're going to go ahead and measure certain things. We're going to go ahead and measure, for example, the distance from the surface down to the top of the cylinder. Okay? So we call this distance, let's say, height top, to the top. Okay? And let's say that going downwards is going to be positive. Positive is measured downwards. So the further you go down, the bigger the number, the deeper you are. And then I'll measure the height from there to the bottom of my cylinder. So we'll call this H, bottom. Okay? Or in this case, I'm just going to use T and B later on to kind of refer to the two. So that means between the two of them, there's going to be a certain difference in the height. The difference in the height is going to be then, of course, the bottom height minus the top height. Okay? So that's going to be a difference in height between the top and the bottom. Also, when you look at this, there's going to be, of course, obviously, a certain pressure due to the water pushing down on this surface up here somewhere. So that means let's call this the pressure now at the top. And there's going to be a pressure at the bottom as well. Okay? Now, in this case, we don't know if they're the same, so let's go ahead and just designate them different, and then we're going to see what happens when we look at the difference between the bottom and the top. So perhaps there's going to be a difference. We'll see. Also, in this case, because there's a pressure here, there's a certain area here, that pressure exerted across this area would then, of course, result in a force pushing downwards. So over here, remember, the pressure always acts perpendicular to a surface in exerting a force on it. So there's now going to be a force, in this case, in the downward direction. Okay, pressure now at the top times the area at the top is now going to give you the force at the top. you now do the same thing over here at the bottom. Okay. In this case, now because the bottom here, the water is underneath it, there's now going to be a force pushing in the upward direction. Okay, upward direction. So over here, there's going to be the pressure at the bottom times the area must equal to the force at the bottom from the fluid pushing up on the surface, okay, of this area right over here. Okay, right over there. So you have two forces acting on the cylinder, one at the top and the bottom. But are those the only forces acting? Well, as it turns out, no. As it turns out, if you look at the cylinder, this cylinder will have a certain amount of mass based on the fact that it is a liquid, it has a density, has a volume. And so now, it turns out, okay, this particular sample here also will have a certain mass equal to the mass density, okay, times the volume. Okay, mass density times the volume. And we are also going to take into account the fact that Pascal's principle is for static fluids. That means that this fluid is not moving. So this cylinder of water is not moving. But in this case, that means that all forces acting on it must cancel out. In other words, the net force must be zero. So there's no net force acting. So how many forces are there? Well, here's a force at the top, here's a force at the bottom, but then of course, based on the mass, there's also going to be what? Force of gravity pulling downwards. Okay? Force of gravity, of course, then it's going to be the mass times gravitational acceleration, g. Okay? So knowing that, let's go and see what happens in this situation. So to analyze this, we now know that, okay, according to the fact that if I have static fluid, that means it's not moving, that means the sum of all the forces must equal to zero. Okay? Sum of the forces must equal to zero. So let's see what that looks like. In this case, 1, 2, 3 forces, okay? This one is going down, so force of gravity is pointing down. Okay, so I'm going to go ahead and call it positive. And then the force at the top is also pointing down, so positive. And then this one is going in the opposite direction, so I have to kind of minus that coming back up. So minus the force at the bottom must equal to 0. Okay? Must equal to 0. Now you can go ahead and put in what I know. So force of gravity is now going to be mass, okay, times g, okay, plus the force at the top is the pressure at the top times the area, a minus here, the pressure at the bottom times the area, and all that must equal to 0. What is the mass again? Well, mass is the mass density, okay, times the volume times g, plus p at the top times area minus p at the bottom times area, equal to 0. Okay. And next thing is volume. I know what volume is. This is just a cylinder, right? If it's the cylinder, that means the volume must then be like the area here multiplied by the length of the cylinder. So this is A times delta H. So in this case, this is going to be mass density times A times delta H times G plus top times area minus bottom times area equal to 0. And notice that each of those terms now will have A here, A here, A here. I can go ahead and divide it out. And so the area actually goes away. Okay? The area doesn't come into play. And then now you have the pressure at the top, pressure at the bottom, and then you now have this part over here. Okay? Now, what I'm going to do is I'm going to go ahead and rearrange this a little bit. I'm going to move, this is negative, move it over to the other side, and then we'll see what happens. Okay? And move this over to the other side as well. So what you find is that pressure at the bottom minus the pressure at the top equals 2. So I'll move both of them to the other side, and I'll leave this over here. Density of the mass density of the water times G times the height difference between the bottom and the top. The bottom and the top. This statement here is Pascal's second law. Okay? So it tells you that, okay, if there is a difference in pressure between 2 points, okay, between the bottom and the top, okay, this is going to be, let's say, the bottom pressure minus the top pressure. That's going to equal to the density times G times the height between those 2 points. Okay? Mass density. So what does that mean? That means that the pressure down here is actually what? Bigger than the pressure up here. So interestingly enough, when you're down here, not only do you feel the pressure from this point up here due to this pressure that's already in existence, but you have to add to it the pressure due to the what? The weight of this water that is also on top of you. Okay, so that kind of gets added onto it. It's added onto it. And that's where this is. Okay? This is. So interesting enough, as you go deeper and deeper, as delta H, the difference between the top and the bottom becomes bigger and bigger, the pressure gets bigger and bigger as well. Okay? Pressure gets bigger. So pressure is directly related to the depth of your fluid. The deeper you are, okay, the more the pressure increases. If you double the depth in, you double the pressure at that point. Okay? So when you're in, for example, a swimming pool, for example, interesting enough, when you're in the swimming pool, when you're in the water, okay, not only do you actually have the air pushing down on the surface of the water, there's already a certain air pressure at the top of the water, but then you have all the weight of the water, okay, on top of you that's going to be pushing down on you as well. Okay? That's the idea. Alrighty. So how do we actually see this in real life in terms of demonstrations? So let's take a look at what this looks like. I'm sure a lot of you have seen this before. What is this? This is actually, okay, a water pump. So what you do is you basically are able to kind of transfer water from one side to the other. And the idea is that if you have a tank over here, some water, you put this into here. The key is that the output must be always what? Lower than what you put this in. So as you begin to pump this, you allow now the weight of the water to kind of push downwards and exit on the other side. Okay? Another way to kind of see this much more readily, is a little easier to see, is this scenario over here. Here I have a graduated cylinder. What I have done is I actually drill some holes on the side of it, okay, in different positions. Okay? So I'm just going to put some water in here. So in this case, as I fill this graduated cylinder with some water, I now have a fluid in here, and this fluid will have now a certain depth. Okay? So notice in this case, the top of the water is now up here. It's up here. And so as you go deeper and deeper now, okay, height, basically delta 8 begins to get bigger and bigger and bigger. The difference between the top and the bottom becomes bigger. That means that according to Pascal's second law, the pressure should now be bigger. Okay? So as the pressure gets bigger, what happens? Well, that means that if you were to try to push water out of it, that means that for every given area, okay, the force that comes out is going to be bigger. So it might look now something like this. So the whole idea is, okay, as you go deeper, okay, the pressure increases with depth. So imagine now if I have this container here, okay, as you go down, so if the top is here, this is on the top, and then as you have these exit points over here, what happens is that as you go down, up here the pressure may be relatively small because you only have a slight difference in height between the top and the bottom. As you go up and down, pressure becomes bigger, becomes bigger, becomes bigger, and becomes bigger. Okay? And as the pressure builds, then what happens? Well, if I were to go ahead and allow these holes to have water exit it, then if each of these holes have the same area, then what you find is if you have the same area here, 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 and here, then the force over here is just pressure times area. But as you go down now, the pressure gets bigger, same area, but the force gets bigger. Okay? As pressure gets bigger still, okay, the force gets bigger, and so on and so forth. As the pressure begins to, oops, I should always have the same area over here. As the pressure begins to get bigger and bigger, okay, the air, we are staying the same, the force gets bigger and bigger. With the same force now, okay, with a different force, that means you'll be able to shoot the water up, okay, more, have more acceleration for the water. So here's what it looks like, okay? So the prediction is obviously that, okay, further down you are, the lower you are, greater pressure, more forceful will the water be coming up. So let's see if that's true. Okay, let's see what happens. And sure enough, as it comes up, you can see that the farthest stream is the one that is further down. Even over here, this is not quite as forceful as that one, due to the increase. Notice as it turns out, it slows up because now the height difference begins to get smaller, the pressure now begins to decrease. Okay? So that's the idea behind Pascal's second law. And this has some very serious consequences as well. Think in terms of, let's say, some mechanical structure that you use for, let's say, holding water back. Look at dams, for example. The very famous dam, of course, is Hoover Dam. Okay? And you look at the way that they construct dams, they actually build it in very specific ways. So when you want to build a structure, a concrete structure to hold back water, what do you want to do? Do you want to go ahead and build a structure that looks like this? So say here's your dam over here, and here's the bottom of the floor, and here is now the water that you want to hold back. Okay? So now the water trying to push against this wall, and you're going to go ahead and build your dam like this. Is that a good design, or do you want to modify this design so that you can now take into account what's going on with Pascal's second law? What is Pascal telling you? I'll leave that up to you to kind of think about. Okay? Alrighty. That's Pascal's principle. Now this can also apply not just to liquid, but also can apply to gases as well, in terms of just, again, any fluid. Any fluid. So let's see what happens in terms of a gas. Well, think about what happens as I'm standing over here. Okay? I am actually surrounded by something that I cannot see. We're actually living in a sea of air. So we're surrounded by air particles. And those air particles are moving and they're slamming into me and they're actually exerting forces on me. okay? And those forces exerted on my body would then exert pressure on my body. So a good question is, what is that pressure like? What kind of pressure are we experiencing when we sit in a sea of air? It's much more obvious when you swim in water, for example. When you're in a sea of water, the water pushing on you, you actually feel that much more readily than feeling air, because air is so much smaller. But it is still there, so we want to kind of see what that might be like. So the way you can think about it is, imagine the following. Imagine if I take a hollow bamboo tube and put it at the top of my head and have it stick all the way up to the top of the atmosphere, okay? So that inside the tube I now have air trapped inside there. And all that air is now moving around, bumping into my head, and really it's the weight of that air, because gravity is pulling on it, as it comes sitting on me, the weight of that air inside that tube is now going to be weighing on me, so to speak, and it will exert a force equal to its weight on my head across a certain area, the diameter of the tube. So let's see what that looks like. You can imagine that somehow if I have, a bamboo tube, I can extend all the way from the bottom, let's say here the sea level right here, all the way to the top. So this is now the top of the atmosphere. Okay, let's see what happens. Well, in this case, let's say the bamboo ball will have an area of, let's say, 1 square centimeter. So it's not that big, 1 square centimeter, something like that. Okay, and let's say that I will basically trap all the air inside of here, and this will stay all the way to the top of the atmosphere. So the question is, how much air is in here? What can I expect in terms of a mass of the air that gets trapped inside? So it turns out, if you have enough air, it actually does have quite an appreciable mass. For example, when you take an airplane, for example, from here to the mainland, not only do you have to bring your luggage and everything along, but you also have to bring a lot of air with you, okay? So you're gonna be bringing a couple tons of air with you inside the compartment of the airplane. If you look at all the space that is inside the air that's inside your refrigerator freezer, for example, if you have a good-sized refrigerator freezer, when you open it up, you see all the air in there. If you take all that air and you were to weigh it, you find that it will have about 1 kilogram worth of mass in there, okay? And that's about the amount of air you can expect inside this tube as well. So you imagine that inside here, the mass of the air that's trapped inside is roughly 1 kilogram, okay? Roughly 1 kilogram. So now I know the mass of the air trapped in there. All that air is now sitting on top of this cross-sectional area down here. The question is, what is the pressure now at this point down here? The pressure, if you recall, is just force of gravity on the air divided by the area down here. So this is now mg divided by A. So m is now 1 kilogram, okay? And then g is roughly on the order of about, let's kind of just round it off just for the sake of this convenience, 10 meters per second squared, okay? So that makes it a little bit easier. And the area in this case is now going to be 1 square centimeter. Now the problem, of course, is that I now have a centimeter over here. So I really want, since I have SI system, I want this to be in meter units as well. So in this case, I can now go ahead and do a conversion. So in this case, I want to go ahead and convert from centimeter square to meter square. Okay, and what you find is that in this case, this is now basically 100 centimeters, and then you square that. Okay, so that means really that's 10 to the 4th power. Okay. 10 to the 4th power, and this will be 1 meter squared. So now when you work this out, you now have 1 times 10 times 10 to the 4th. This is really what 1 times 10 to the 5th now. And the units now, kilogram meter per second squared is Newton divided by meter squared. Okay? If you recall, Newton per meter squared is now called Pascal. This is now 1 times 10 to the 5th pascals. Okay? Or roughly 100 kilopascals. So as it turns out, this is actually not that bad of an estimate. In general, what we find is that if we were to look at the amount of pressure that the atmosphere is exerting on us near the surface of the Earth, at sea level, for example, that number is actually pretty close to this. We call that number the atmospheric pressure, okay? The atmospheric pressure. And we're going to define it as a single number. Let's go ahead and get rid of this. That number is usually called 1 atmosphere. So by definition, we find that on the average, okay, the pressure due to the atmosphere at sea level is defined as 1 ATM, 1 atmosphere, and it actually has a value of 1.013, I believe. 1.013 times 10 to the 5th, pascals. Okay. Now, of course, in this case, it's a really big number, and even for us, Pascal doesn't really have much meaning. So we can actually translate it and use an equivalency in US customary system. You're going to go ahead and express this atmospheric pressure due to the air pressing down on us, okay, at sea level. This is roughly 14.7, okay, psi, pounds per square inch. Okay, pounds per square inch. That means that as I'm standing here, every square inch of my body is now experiencing a force of about roughly 15 pounds from the air pushing on it. Okay, that's per square inch. And imagine how many square inches do you have across your body. Then you actually find the total force that's acting on you based on the formula force is pressure times the area. And so I'll leave that exercise up to you to see how much force is actually acting on you based on the atmosphere pushing down on you. And that seems like a pretty big number. So how come we don't feel it? Well, lucky for us, as it turns out, remember that force is due to the air pushing on, let's say, our skin, our surface. Okay? And it's going to try to push my skin inward. But guess what? On the other side of the skin, I also have what? The rest of my body. So I have flesh and fluids inside my body. And as it turns out, that also exerts a pressure that tries to push the skin back out. And it just so happens that since we're basically born into this environment, we have adapted to this atmospheric pressure. So the internal pressure of my body pushing back outwards across my skin is also about 14.7 pounds per square inch. So those two pressures basically create forces that are now equal and opposite. And so they cancel out at the surface of my skin and I don't feel any difference. The only time I feel it is when there is a difference in pressure between the inside of my body and the outside. And so as I dive deeper and deeper into water, for example, in a swimming pool, then in addition to the atmospheric pressure pushing down, I also have the weight of the water. That's when I begin to feel that, oh, something's not pushing my head inward. And that doesn't feel comfortable. On the other hand, as you go ahead and get into an airplane and you go up higher and higher, what you find is that as you go up higher and higher up, that means that you have now less air above you pushing down. The weight is going to be less. That means the pressure gets lower as well. Because remember talking about the idea of Pascal's second law? The deeper you are, the greater the pressure. So this is the top of your atmosphere, the top of your fluid. So as you go deeper and deeper, it gets greater. So when you're closer to the surface, you have a lower pressure. So that's when you kind of feel your ear popping. That's because now the higher pressure of your body pushing outward will now cause a net force pushing your skin outward. And that's what you're feeling, okay? So you have two different scenarios, okay? You can either feel pressure pushing you in or pressure, okay, pushing your skin outwards based on outside pressure difference relative to your inside. All right, so that's atmospheric pressure, okay? And you actually see this atmospheric pressure quite a bit in terms of different kinds of applications. One very simple application, of course, is something that looks like this. Of course, a lot of times, we know this as a suction cup, right? You take this, you go boom, and it's sucking itself onto the surface there. As it turns out, that's not quite true, okay? That's a little bit of a misnomer. In physics, okay, we never suck in physics. Okay? In this case, it is not due to something that's sucking. As it turns out, it is due to the fact that, okay, there is a difference in pressure between the top of the device and the bottom of the device. And that's due to atmospheric pressure. So the way this works, if you look at a suction cup, there's a little concave surface on the inside. So that means there's a little bit of air that usually is going to be sitting there. So if I'm going to just put it on a surface like this, what will happen is that the air underneath, okay, the cup is going to be pushing upward with a certain atmospheric pressure, and the air on top pushing down on it will also have the same atmospheric pressure. So there's no net difference in pressure, so that means there's no net force acting on it. I can kind of move it very easily. I can now just overcome the weight of this, I can move it. Here's what happens. When I take this now and I push down on it, I now squeeze the air out from underneath it. So now all of a sudden, there's very little air underneath. If there's no air underneath, it can't push against the bottom, and it cannot exert pressure and therefore a force on the bottom. So all of a sudden, the pressure inside the cup now begins to get very, very small. And if I can squeeze all the air out, it basically becomes zero. Okay? And that means now I have pressure on the outside of 14.7 pounds per square inch pushing downwards on the suction cup. That's what's holding the cup against the surface. So as I squeeze this down, that's when I try to lift up. Very difficult to lift up at that point, okay? Because now I have to overcome the air that is sitting on it, okay? And I have to overcome that force, okay, that's holding it in surface. So how do I do it? Well, I do it by letting air help me as well. So if I were to go ahead and release this, okay, connection and allow air to kind of escape back inside, that air now will push back with a force that is equal to 14.7 pounds per square inch per unit area, and that'll give you a net force, and that'll make it easy to lift up on it. So you can actually do things like this where you actually lift up pretty heavy objects based on the fact that there's going to be a force acting on it due to difference in pressure between the top and the bottom. Okay? So this is really not due to any sucking, it has to do with atmospheric pressure. That means that this should not work when there's no atmosphere. So you were to take this to the moon, for example, you would not be able to use this okay, for any practical reasons. Because when you try to push down on something, there's no difference in pressure, it will just come right off. There's no difference. Okay? And you can see it in other kind of scenario. Here's a real cool application. This is actually like a little skirt you can put onto a soda can. What it does, it then sits in the bottom and allows you to kind of squeeze the air out from underneath the skirt. And as you do so, there's now a net difference in pressure between the top of the air sitting on the skirt and vertical air underneath. So this now allows it to kind of stay in place and you won't get knocked off. So if you're in a plane or an air or a boat that kind of rocks back and forth, you now use this to kind of hold your drink to the surface of the table and not have to worry about it spilling and turning over. Some of you may notice that if you look at construction sites, for example, there are these huge yellow, orange barrels with a skirt, a black skirt on the bottom. Guess what that skirt is used for? Okay, think about that. You have other things you can use this for. This is actually a device that allows you to change light bulbs in a high ceiling, for example. So here is, again, that idea of a suction cup, but it uses atmospheric pressure. So if I have a light bulb here, I can now push onto here, squeeze the air out from underneath it. I create now a semi-vacuum inside, create a pressure on the outside, holding this now against the surface there. And you can now take the air, turn it in. And notice there's a little string here. What do you think the string is for? Well, the string is so that you can release the vacuum. So as I pull on the string, I allow air to kind of get underneath the object, and as I put enough air under there, it will then pop right off when the pressure balances out on both sides of the suction cup. Okay? A lot of different applications. Okay? So you can see that. All right, so at this point, I'm going to go ahead and stop here, and we'll continue with our next session when we talk about one last thing, looking at measuring atmospheric pressure, a little bit of continuation, and then we'll move on to a brand new principle called Archimedes' principle. That tells you something about whether an object, when it is basically interacting with a fluid, whether it will float on top of the fluid or it will sink in the fluid. So Archimedes' principle is going to be our next topic. Okay, and until next time, take care.